Right now. The GPS in your phone is correcting for the fact that time moves differently in orbit than it does on the ground. Without that correction, made every single day, your GPS would be off by 11 kilometers. We are correcting for Albert Einstein's general relativity, daily, without thinking about it. And if that is true near Earth, near a black hole, where gravity is incomprehensibly stronger, something far more extreme happens to time. In this video, I am going to show you exactly what happens to time inside a black hole. The real physics, not the dumbed-down version. What Einstein proved in 1915, what the 2019 photograph confirmed, and what happens, second by second, if you fall in. And I'll warn you, the answer changes how time feels. In 1915, Albert Einstein published his general theory of relativity. The core idea, gravity is not a force. It is a curvature in space-time. And here is the part that changes everything. The stronger the gravity, the slower time passes. Not slower for some people, slower for everyone, universally, measurably. Time itself runs at different rates, depending on where you are in a gravitational field. GPS satellites orbit at 20,200 kilometers altitude, where Earth's gravity is weaker than on the surface. Two effects compete. The satellite's speed makes its clock run slower. The weaker gravity makes it run faster. The net result, satellite clocks run about 38 microseconds fast per day compared to clocks on Earth. 38 microseconds sounds tiny, but at the speed of light, that translates to 11 kilometers of position error per day. So GPS engineers correct for general relativity every single day. If they did not, the system would be useless within hours. Einstein, writing in 1915, was right enough that we stake billion-dollar infrastructure on his mathematics 110 years later. So if gravity near Earth causes measurable time differences, what happens near an object with gravity so powerful that not even light can escape? What happens to time near a black hole? A black hole is a region of space where matter has collapsed to such extreme density that the escape velocity exceeds the speed of light. Nothing escapes, not matter, not radiation, not light. The boundary is called the event horizon. Cross it, and from the perspective of the outside universe, you are gone. In 2019, the Event Horizon Telescope collaboration released the first actual photograph of a black hole, the M87 galaxy, a black hole 6.5 billion times the mass of our Sun. That orange ring of light around the dark center, that is matter heated to billions of degrees, orbiting at nearly the speed of light, right at the edge of the event horizon. Now, what happens to time near this object? Einstein's equations tell us exactly. As you approach the event horizon, from the perspective of someone watching you from far away, time slows for you. You appear to move slower. Your clock ticks slower. The closer you get, the more extreme this becomes. 1 hour at a safe distance from a stellar black hole could equal several years on Earth, depending on proximity. At the event horizon itself, time dilation becomes infinite. From the outside observer's perspective, you never cross the horizon. You appear to slow down, redshift into infrared, and freeze. Forever, like a photograph. You are still there, at the moment of crossing, as far as the outside universe is concerned, for eternity. But here is where it gets genuinely disturbing. That is what the outside observer sees. What do you experience? From your own frame of reference, crossing the event horizon is not dramatic, at least not immediately. If the black hole is large enough, and some are billions of times more massive than our Sun, the tidal forces at the horizon might be gentle enough that you cross without immediately feeling anything catastrophic. You look back. Earth is still there. The universe is still there. Slightly blue-shifted from your acceleration, but visible. You have crossed the event horizon, and the universe outside has not ended. But here is what has ended. Your ability to send any signal out, any light you emit, any radio wave, any message, it falls inward with you. Nothing crosses back. From this moment, for the outside universe, you have ceased to exist. As you fall deeper, the tidal forces become extreme. The gravity pulling on your feet is now measurably stronger than the gravity pulling on your head. You are being stretched, vertically, and compressed, horizontally. Physicists call this spaghettification. Not poetically, literally. You are being pulled into a strand. For a stellar mass black hole, this happens before you reach the horizon. For a supermassive black hole, it happens much deeper inside, after crossing. Either way, the end is the same. At the singularity, the center, all known physics breaks down. Our equations stop working. We do not know what happens. The singularity is the edge of human knowledge. Literally. One final thing. Stephen Hawking predicted that black holes are not actually permanent. Quantum effects near the event horizon cause particles to slowly leak away, what we call Hawking radiation. Over an incomprehensibly long timescale, a stellar black hole would completely evaporate. What happens to everything that fell in? We do not know. This is the black hole information paradox, one of the most actively debated problems in theoretical physics today. Here is what I keep coming back to. Time is not a backdrop. It is not a container that everything happens inside of. It is a physical thing. It bends. It stretches. It stops. The reason this matters, beyond the physics, is that it changes what now means. When I look at the M87 black hole photograph, I am seeing light that left that region 55 million years ago. At the event horizon, time has stopped. But from my perspective, it is happening right now. Is that now real? Is my now real? Is there a universal now at all? Einstein's answer: no. There is no universal present moment. There is only the present moment as experienced from a specific point in space-time. Every observer has their own now, and they are all equally valid. I want to ask you something before you leave. Does knowing that time is relative, that it bends near massive objects, that there is no universal now, change how you experience your own time? Your life is a specific path through space-time. Nobody else has your exact path. Nobody else experiences your exact now. Does that feel lonely or extraordinary? I genuinely do not know my own answer, and I have been thinking about it for a week. Tell me yours below. I read every single one. Sunday, a 30-second short. In 2019, we photographed a black hole for the first time in human history. The image took 8 petabytes of data to produce, so much that it could not be sent over the internet. How they actually got that image to scientists around the world is one of the most quietly extraordinary stories in recent science. Thursday 6 p.m. Vibeverse.